Euclid's Elements, Book 3, Proposition 1, a remarkable diagram. My motto? Plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. After watching the above video by the world's greatest self-acclaimed mathematician, I had to agree that I found the proof to be somewhat futile, and what I saw as a poor attempt at reductio ad absurdum, by assuming something to be what it wasn't, namely the centre of the circle. I did not agree that the proposition was unremarkable and unnecessary. On the contrary, I consider the diagram consisting only of a circle, a chord, and the bisector of the chord to be quite remarkable, because of what can be deduced from it, without much embellishment. To prove the proposition, all that was necessary was to draw straight lines joining the ends of the chord and bisector as shown to form the kite. Having formed the kite, we can say that a. By construction, the two halves of the chord are equal. b. The bisector being perpendicular to the chord, the four angles at the point of intersection are all right angles. c. We have four right angle triangles, two large and two small. d. A half chord is one side of the right angle of the four triangles. e. The two large triangles share the largest segment of the bisector as the second side about the right angle. f. The two small triangles share the smaller segment of the bisector as the second side about the right angle. g. The two small triangles are congruent, and the two large triangles are also congruent. Book 1, Proposition 4. h. The two very large triangles formed by a small plus a large one are on opposite sides of the bisector line, so the two sectors formed are identical and therefore constitute a semicircle. The bisector is therefore a diameter, so after bisection the point of intersection is the centre of the circle. QED. Corollary 1. Now all four triangles being similar, the two final triangles are right-angled triangles, and since this is true for any point on a diameter, we can categorically state that all triangles in a semicircle having the diameter as one side will always have a right angle touching the circumference. QEF. Now taking our basic diagram and labelling the two parts of the diameter A and B, we can draw a radius from the centre of the circle O to point P, and which will have length A plus B all over 2. The length of the segment OC is equal to A plus B all divided by 2 minus B is equal to A divided by 2 plus B divided by 2 minus B divided by 2 minus B divided by 2 is equal to A minus B all divided by 2. By the quarter squares rule, A plus B all divided by 2 squared minus A minus B all divided by 2 squared is equal to the square root of AB squared. Book 2, Proposition 8. Corollary 2. Since A plus B can be any magnitude and can be divided into any number of AB pairs, we can say without contradiction that the square on the hypotenuse is equal to the sum of the squares on the other two sides, the Pythagoras theorem. Corollary 3. Now, square root of AB squared equals AB, so we can complete the square on PC and construct the rectangle on A equal to AB. Starting with any rectilinear figure, we can convert it to a rectangle of equal area, which can then be used to construct the diagram and obtain a square of equal area, rational or irrational. This is Book 2, Proposition 14. That these operations can be carried out using just ruler and compass is fundamental to modern mathematics. Also, by ruling a circle to generate a line equal in length to half the circumference, we can square the circle. It truly is a remarkable diagram.